G'day, Richard Marr from Mars Classes. Going to look at a real famous physics equation today. That's E equals mc squared. I'm sure most of you have been told by teachers that it's the mass-energy equivalence equation. It shows that mass and energy are different sides of the same coin. The problem is they haven't been telling you the whole truth. There's a bit more to it than that. But what we're going to do today is we're going to have a look at some algebra, pretty straightforward algebra, to find out a few things, to find out that it's not just mass and energy equivalence, there's actually momentum involved as well, and to give an explanation as to why, if any object has mass, it is impossible for it to get to the speed of light, and a few other things. So first up, let's just see if we can derive E equals mc squared, and we'll try and be clever with this and see if we can do it. We know that work done is by a force when it moves an object is the magnitude of the force times the displacement in the direction of the force, and we know that force is equivalent to mass times acceleration. Newton told us that one. So we can then also look at what acceleration is, and we know that's the rate of change of velocity. We can substitute that into the equation, and then we can simplify this equation down. We end up with work equals mass times velocity squared. Now we know that work is energy, work done is energy expended, and we know that the speed of light is a velocity, so look what we've got there. We've got E equals mc squared. Aren't we clever? However, Einstein was getting sick of telling people that E equals mc squared is not the whole picture. It's just when a mass is stationary relative to you. When a mass and you are in the same inertial frame, and that mass is stationary relative to you, we can say E equals mc squared. Because when masses move, the mass dilates, just like time dilates, or just like length contracts. And it does it by the same gamma factor. So when we look at relativistic mass, it is the rest mass, or the mass of an object which is the same inertial frame as you, divided by the gamma factor. So once we incorporate that into the equation, we actually get a complete mass-energy momentum equivalence. And when you look at it, there's one term which is squared, and it's the same as the sum of two other terms which are squared. Now that looks very similar to the Pythagorean right triangle theorem. So let's utilise a right triangle to help us understand what's going on with this. Now remember I said Einstein kept stating that if a mass was stationary relative to you, E would equal mc squared. Now if it is stationary relative to you, it's not going to have any momentum. So that blue leg of the triangle would reduce to zero, and yeah, E would equal mc squared. So that works really quite well. If we look at another version of things, something that has no mass, like a photon. If something has no mass, the mc squared side would go to zero, and the energy would be equal to the momentum times the speed of light. So that's another little interesting thing we can find from that massless objects can move at the speed of light. So let's start doing the algebra. Now, what I'm going to do is that equation at the top, I'm just going to get the square root of it, and then put a couple of terms in the middle, because we've still got E equals the square root of all that information there, but it also equals mc squared, and the gamma factor times the rest mass c squared. So once we've got all that information, if I then square it all, it'll be the same as what it was at the top with those few other terms in there. Now if I take the last term away from the the E squared on the left, I get E squared, take rest mass squared, speed of light to the power 4 equals p squared c squared. That's pretty reasonable. But the rest mass squared times c to the power 4, we know that that is equivalent to the energy squared divided by the gamma factor squared. So if I substitute that in, I get that expression there. Now, if I divide every term by energy squared, I can simplify it down to this thing here. Now, if we look at the PC on E squared, that's equivalent to V on C all squared. I'll just simplify that down a bit, and we'll get that value in there. Now, I'll move that up the top and just take the square root of each side, and we get that, and then I'll rearrange it, and we'll get V equals C times momentum times speed of light on E. Now why have I done that? I've done that because we're looking at V equals the speed of light times some factor, and the factor is PC on E. Now you'll notice that the triangle I've got drawn there, PC is not as big as E. So the ratio of PC to E is less than 1. And no matter how small I make that mass, I'll never get PC to be smaller, to be the same size as E. It will always be smaller than E. So that factor PC on E will always be less than 1. So the velocity of any mass has to be less than the speed of light. It'll get very close to it if it's a small mass, but it has to be less than the speed of light. It's not possible to be anything else. Okay, so that's fair enough for something with mass. Now let's consider when we mention things that have no mass. If it's got no mass, E would equal PC. And this is, we're looking at a photon. Now, de Broglie had the de Broglie wavelength. It was stated as Planck's constant on P. Or we can rearrange that and say, the momentum is Planck's constant on lambda, or the wavelength. Now, if we substitute that into the equation which says E equals PC, and instead of P we put H on lambda, what do we get? My God, we've got the equation E equals HF. Pretty neat, isn't it? So that's the equation which Planck has used to help us understand the quantization nature of light. Okay, I'll leave it at that for today, and you can have some time to think that one through.